So, and WT. Okay, so this is the AR2 model that I give, and I tell you that the PACF1 is equal to 0.86, and the PACF2 is equal to negative 0.75. Okay, and recall that from our definition, that's the partial autocorrelation is that's the autocorrelation, the conditional autocorrelation, right? So, and if it's a linear model, then the partial correlation, say like the partial autocorrelation of say like xt and xt minus 2 is just the coefficient of xt minus 2, right? So you can see that right now here we have the PACF we calculate from the data is negative 0.75, and we can also see the coefficients is in the regression model is also negative 0.75. Okay. Yeah, but some of you notice that the PACF 1.86 is not equal to 1.5. Okay, so the partial autocorrelation of xt and xt minus 1 from what we've got from the data and what we got from the regression model are different. So someone asks me this question, so why they are different? So I think that's a very good question. And the reason is that the PACF is the partial autocorrelation function. It's a conditional correlation. Okay, so the PACF1 of xt and xt minus 1, if you want to express in the regression, is the coefficient of xt equal to say some like beta xt minus 1 plus wt. Is a coefficient of xt minus 1 of this regression model. So this regression model does not contain xt minus 2. Okay. Yeah, so if you want to find the PACF and xt minus 1, you just run the regression of xt and xt minus 1. The coefficient in front of xt minus 1 is your PACF 1. Okay, this 1.5 is not your PACF 1. Okay, because it conditions on xt minus 2, but that's not the thing we want. Okay, that's not the thing we want for the autocorrelation between the conditional autocorrelation between xt and xt minus 1. Okay, so this regression, the first regression, is only informative of PACF2. Okay, so which is the autocorrelation between xt and xt minus 2 conditioned on xt minus 1. Okay. Yeah, so that's a difference. So that's why you find 0.86 is different as 1.5. However, if you just run this regression, then the beta you got have to be 6. Okay, you can generate a data by yourself and make sure that you can got this. Okay. Okay, so now let's move on. So let me erase this. And let's begin today's class. Okay, so today's 3.8. Okay. So we will do a lot today. Okay, so the R is okay. So let's continue our discussion of the PACF, the partial autocorrelation function. Okay, so we discussed the, so just recall PACF. So recall for ARP model, the PACF of order H is equal to 0 if H is larger than P. okay? And provides the intuition of why this is the case in last class. The intuition is that basically is that when you want to study the PACFH of order H, then in the regression model, since you do not like include xt minus h in your regression model, so that means that coefficient have to be 0. So that means the PACF of h is equal to 0 if h is larger than p. So that's the intuition. Yeah, and I think I won't give the proof of that here, because I think that's not that important here. So now let's do the MAQ, okay? Do the MAQ. So the MAQ model. So since now we are just record the definition of the ARMA model, we want the model to be both causal and invertible. So since our like ARMA setup, the MAQ is invertible. But this is not always the case, okay? So not all the MAQ model are invertible, but the MAQ model we focus in this class, or we focus in the ARMA part of this class, is invertible, okay? So since this MAQ is invertible, then we can write it as a infinite AR representation. So this is the AR infinity representation. Okay. Okay, so you can see that the invertible comes in again. So it's a very, 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 very useful property, and it helps us a lot. Okay. Yeah. So in your analysis, you need to check that your ARMA model is causal and invertible. Otherwise, like all we do here is not correct. Okay, so all we do here about the ACF and the PACF are not correct. Okay, so let's see if, let's assume that if J is from 1 to P, okay, so instead of J from 1 to infinity, we assume now, let's just consider the case that J is from 1 to P, okay, and this P is less than infinite. Okay. And you can realize that this is a AR infinity model, okay? And if we have like a P combination of the X legs, then from our ARP result, we know that the PACFH is equal to 0 if H is larger than P, okay? So this is just the results that we got from our ARP model. Okay, so if we only have a finite combination, if we only use a finite combination of the X legs to explain X, okay, then then the PACF of order H would be equal to 0 if H is larger than the order of our AR model. Okay. But unfortunately, here you can see that our J is not go from P. Our J is go to infinite. Okay. So, but J now goes to infinite. We are having this AR infinite representation. Okay. So that means no cutoff of PACF for the MAQ model. So that's the result. So for the ARP model, we know the PACF cuts off at order P, but unfortunately for the MAQ model, we cannot find a cutoff for it. Okay. And to show this, it's very easy. We just write the MAQ into its AR infinite representation and use the argument of the ARP model to find the cutoff of the MAQ model. But unfortunately, we see that we cannot find a cutoff point. Okay. So let's see an example. Okay. So let's see an example of MA1. Okay, so MA1 is xt equal to WT plus theta, WT minus 1. Okay, and this theta, since we want it to be an inverted model, so then this the absolute value of this theta going to be less than 1 and larger than 0. Okay, so it can be shown the PACF of this MA1 model is equal to this. So if it's h is larger and equal to 1, then this is the PACFH. Okay, so it's a function of theta and a function of h. Plus 1. So a couple of observations here. So clearly we can see that number 1. So since theta is less than 1 and larger than 0, so that means the numerator. So the numerator is this. So the numerator is never equal to 0. Okay, so the numerator is never equal to 0. So that means the PACFH never equal to 0. Okay. And this definitely is consistent with our result of the MAQ model. So for any MAQ model, we cannot find a cutoff point, okay, for the PACF. Okay, so we can easily see from this example definitely is consistent with our result. Okay. And observation number 2. Okay. But this, like PACF, would still provide us some information about the MAQ model. So as h goes to infinity, we can see minus theta h. Let me see, minus, no. Yeah, minus theta h goes to 0, right? Right. So this implies numerator goes to 0. Okay. And 1 minus theta 2 to the power 2 times h plus 1 goes to 1. Okay. So that implies the denominator goes to 1 as h goes to infinity. Okay. And combining the numerator results and the denominator results, we can say that the PACFH goes to 0 as h goes to infinity. Okay. So even though we cannot find a cutoff point for the PACF of the MA model, especially of this MA1 model, but we can know that the PACF would decrease all the way to 0 if the lag, if h goes to infinity. Okay. Yeah, so in other words, this says that PACF tails off. Sometimes said that decreases to 0. Okay. So now here's our like final result, and I actually show this result in a few lectures early. So this is our final results, and we will use this table to decide the order of our model. Okay. Okay. So we have this like 2 times 3 table. Okay. So for the ARP model, the ACF, it tails off. The PACF, it cuts off after. For the MAQ model, it cuts off after Q. The PACF tails off. For the RMRPQ, unfortunately, both ACF and PACF tails off. So this table I've shown you a few classes early, and yeah, this is a table. Yeah, and I won't show the slides here, but you can find examples. So you can find the examples of different AR, the PACF and ACF of different AR-MAPQ model from like slides 31 to 33 of chapter 3. Okay, and of course you can also generate different AR and MA models and generate those ACF and the PACF plots and find that, or to reassure yourself that you actually can got the results from this table. Okay. So any questions? Okay. So I think this should be good. It should be all good with this. Okay, so now let me switch back to the R and let me run some codes, the ACF and the PACF codes for you. So let me switch. Share screen. So this is today's R. Okay, so the first example is that I plot some ACF plots. Okay. All right. So this is the an ACF plot of a AR model, and this AR is an AR2 model. The coefficients are 1.5 and negative 0.75. Yeah, so which is a model, the example that I gave early. Okay. All right. So this code ARMA ACF is to obtain the ACF plot, to obtain the ACF. From an AR MA model. Okay, and then we plot it. Okay, so this is to plot ACF. Okay, so you can see this plot is the ACF plot of this AR2 model, and you can see that we do not find a this plot is not that good because it does not have a clear confidence interval. Okay, but you can definitely add the confidence interval here, I think. So the confidence interval here is 2 over square root of 50 because we generated 50. No, sorry. Yeah, it's not that informative, I think. Yeah, but anyway, yeah, because I don't think I have the number of observations here. So yeah, but anyway, you can see that it's like this ACF plot of this AR2 model tails off, okay, because it like decreases all the way to 0 as we increases our legs. And certainly there's like no clear cutoffs in this ACF plot, okay? So this is exactly the same as our result from the table. So the ACF of an AR model tails off, does not have a clear cutoff. Okay. And now the second part of this example just obtains the PACF from this AR2 model. Okay. Okay, and let's run this code. All right. Yeah, I think this, let me change the name to PACF. Let me rerun this. Okay, so this becomes PACF, which is correct. Okay, yeah, so to obtain the PACF, like the thing here is that you just add this PACF equal to true in this ARMA ACF command, okay? But if you want to get the ACF, you just like do not have this part of the code. So I think the default of this PACF is just PACF equal to false. So that's the default of this command in this ARMA ACF command. Okay, so now you obtain the PACF from this ARMA model and we plot it, and this is what we got. Okay, so you can very easily see that we only have 2 PACF that are not equal to 0. Okay, so the PACF cuts off at 2. Okay, and this is exactly what we have from our results. So from our results, we know that if we are considering a AR2 model, then the PACF should cut off at leg number 2. Okay, and this is exactly what we got. And the ACF plots of this AR2 model is again exactly the same with our results. So we do not find a clear cutoff point, but we do see a decreasing pattern of the ACF plots. Okay. Yeah, so from you can like, so here I only consider the model, AR2 model, and maybe after class, you can try to consider a MA model or a ARMA model. And for the MA model, I think you will find exactly the same results as our table. So the ACF cuts off at order number Q, but the PACF does not have cutoff point, but it will decrease to 0. And for the ARMA model, you won't find any cutoff points from the ACF and the PACF plots, but you will find the ACF and the PACF decreases to 0. It tails off. Okay. Yeah, so you can try to change the coefficients of this code and see how the ACF and the PACF change. Okay, so any questions? Okay, so now if there's no questions, let's do a real data example. Okay, so this data is the data that we have seen a lot in previous class. So this is a recruitment data. Okay, so we first plot the ACF and the PACF of this recruitment data, and we finds 48 observations, the 48 legs. Okay, so the 48 legs of ACF and PACF of recruitment data. Okay, so let's check the ACF and the PACF plot. Okay, so for the ACF plot, we find that there's no clear cutoff point, or even though you can say that maybe 1, 2, 3, 4, 5, 6, 7, 8, 8 might be a cutoff point, but we notice that like in maybe here in the legs here, those ACF again becomes like jumps out of the confidence intervals. Okay, so that means the cutoff point 8 here might not be a good choice, because we find like a bunch of like ACF legs that are outside the confidence interval after leg number 8. Okay, so for this plot, we might say that this is a plot that tails off to 0. Okay, so you can see that it's somewhat like follows a tails off pattern instead of a cutoff point pattern. Okay. However, for the PACF plot, we can see that for leg number 2, leg number 1 and leg number 2 are certainly outside of this confidence interval. And after leg number 2, we do not find like a lot of legs that are outside this confidence interval. Okay, even though there are some of them like out of the confidence interval, but it is not as large as like the ACF plot, right? Yeah, so this to me, or I mean to most people, this is more like the PACF cutoff at leg number 2. Okay, while this ACF tails off. Okay, so just by looking at the ACF and the PACF plot, and by looking at by checking our table, we can see a AR2 model. AR2 model might be a good choice, right? The AR2 model might be a good choice, right? Yeah, but I mean, obviously, like different people have different views on the ACF and the PACF plot. So I don't know. So some people might also think that this PACF tails off. Yes, ACF, the PACF tails off and the PACF tails off, and they consider this might be a ARMA model. Yeah, so I mean, in your final project, and of course in any of your research, you like this AR2 model is just a starting point. Okay, once we fit this AR2 model, we check like the residuals, we check the coefficients, and if the residuals and the coefficients are not very good, I think you might change to maybe an ARMA model or a MA model. Okay, and more importantly, if I don't know, if if you change to those models and the BIC becomes smaller, okay, then you might think like your starting point AR2 model is not a good model. Yeah. So anyway, so the AR2 model is just a good starting point, and for the representation purpose, we will just like stick on this AR2 model. Yeah, but a good starting point. Okay. Yeah, but I mean, in your analysis, I want you to do like all those model comparison or model selection process. Okay, so now let's say, okay, we will just use this AR2 model and we want to fit this model. Okay, so to fit this model, we use this code called AR.OLS. So even though this is not a very good code, we will discuss more about like the estimation later. But for now, let's just use this AR.OLS code. So it's like the AR-OLS regression. Okay, and here we use the recruitment data. The order is number 2 because we consider AR2 model. We do not demean the data, so we need to include the intercept. Okay, but if you do demean the data, you can either include the intercept or not include the intercept. Okay, so if you demean the data and if you include the intercept, the estimator of the intercept is going to be 0. Okay, and it is insignificantly different from 0. Okay, and if you do not include the data, if you do not include the intercept, that's totally fine. Okay, but if you do not demean the data, so that's the key. So if you do not demean the data, then you need always to include your intercept. Okay, yeah, otherwise you will change the assumptions of the OLS regression. Okay, so now let's do this regression and let's see the regression results. Okay, so here's our regression results. The intercept is about like 6.7. The coefficient 1 is 1.35. The coefficient 2 is negative 0.46. Okay. So we got our AR model like xt equal to 6737 plus 1.3541 x t minus 1 minus 0.4636 x t minus 2. Okay, so this is our regression results. And yeah, so then the next step is to do some model analysis. I mean, to check the results of this model. So we plot the residue. We do the residual plots because we know that if our model is a correct model, then the residual plot is going to be more like a white noise, somewhat like a white noise. So everything of the ACF and the PACF should be within the confidence interval. Okay, so here's what we got. So the first is the ACF plot of the residues, and the second plot is the PACF of the residual plots. And you can see that most of the plots looks good. Okay, so most of them are within the confidence interval. Okay. However, we notice that for at leg number 1, leg number 2, leg number 3, and also leg number 4, both ACF and the PACF, those legs are outside the confidence interval. Okay. And this is also true for the legs, say like leg 0.5, legs 1.5, maybe around 2.5, 3.5, and similarly for the PACF plot. So at leg like 1.5, 1, 2.5, 2, 3.5, 3, 4.5, and 4, we find that the ACF and the PACF of the residues are outside these confidence intervals. Okay, so this suggests that we might have some seasonality problems here. Okay, so those patterns just comes every like 0.5 legs. Okay, so 0.5 here is just 6 months. Okay, because we are doing a yearly data, so 0.5 is 6 months. Okay, so it comes on and on like every 6 months. So this suggests that we might have a seasonality problem. Okay, but we haven't covered to the seasonality problem here yet. We will move to the seasonality stuff like later in this class. Okay, yeah. So here what we got is residual plots good for most part, but there are some seasonality patterns. Okay. So this just says the residual plots are good, but it's not perfect. There is still some improvement we can do to our model. Okay, so that's the residual plots check. And let's also check the AR coefficient. Let's check whether this is a causal and an invertible model. Okay, so in order to be a causal model, causal inverted model, so in order to be a valid ARMA model, we want the roots are within 1. Okay. However, we found the roots here are, one of them is within 1, this unit circle, but the other one is outside this unit circle. Okay, 3.5, which is definitely not good. Okay. Okay, and we can confirm ourselves if we change this to a infinite MA process, and we find that the coefficient actually diverge. Instead of converging to 0, it diverged to infinite. So from here, you can see that couple of things you observe. So first, this might not be a very, very good model, even though it is a very good starting point by looking at the ACF and the PACF plot. But we observe, but if we fit this model by the software, we find that it is actually not a valid ARMA model, okay? The coefficients are not valid. And moreover, we find that there is some seasonality in our residual plots, okay? So from here, we might think that this AR2 model might not be a very good model. We perhaps want to include, say, like MA terms, or we perhaps also want to include some seasonality parts in this model. Okay. Okay. Yeah, so for the seasonality part, we will cover that later in this class. But for now, you can just try yourself, try different AR and MA model yourself, and check the check the residuals and the coefficients of those new models. Okay. Yeah, and I think you might find a valid ARMA model, but if you do not include the seasonality pattern, you cannot get rid of this seasonality stuff here. Okay. Yeah, we'll talk more about that later. Okay, so any questions of this example? Okay, so if there's no questions, I think I want to move to the next part of this ARMA model. So for now, we discussed like the theories of the ARMA model. So what is a valid ARMA model? We wanted to have like that ARMA setup. We want it to be causal. We want it to be invertible. And we know how we can check we know how to check it is a inverting model and it's a causal model. Okay, so that's the theory of the ARMA. And then we move to the ACF and the PACF plots of the ARMA, and we know that how we can decide the orders of the ARMA by looking at the ACF and the PACF. Okay, so the next question is that once we decide the model, how we can estimate that model. Okay, so suppose that now we decide that we have a model, say like AR2, or say like ARMA21, how we can estimate this model. Okay, so we use like this, you can see we use this AR .ols command here, but this is not good for the model that has a MA part. So you can just read from this syntax. It's just doing the AR regression. So it does not include the MA part. Okay, so the next question we want to do is to do the estimation. So how we can do the estimation. Okay, and so today I want to talk about the estimation, and I think I might have time to talk about the forecasting, so which is the last part of this ARMA model, and which is also a very important part. Okay, so now let me move to the whiteboard to discuss the estimation of this ARMA model. Okay. ARMA estimation. Yeah, so as you can imagine, there are a lot of ways to estimate this ARMA model. Just as simple linear regression. Just as a regression model, you have a bunch of ways to estimate the regression model. You can use, say, like the maximum likelihood by assuming the distribution of the error term. You can just use like the OLS, which is to minimize the square of the residues. You can also use like the moment estimation. You can also use like the generalized moment estimation. So there are a bunch of ways to estimate the simple regression model. And here is the same thing. So there are a lot of ways to do this ARMA estimation. And for this class, I think I will just introduce this called like the unconditional least square, or sometimes you can think of it as a special case of the maximum likelihood estimation. Okay, because the reason is that like the codes that I give you is basically built up on this unconditional least square estimation. Okay, so we focus on unconditional least square. This is a special case of the MLE. MLE stands for the maximum likelihood estimation. If you do not know that, that's totally fine. This is basically to maximize the likelihood of your estimate. Okay, so that's totally fine if you do not know that. Okay, so we will just do a unconditional least square estimation here. Okay, so this unconditional least square is pretty much similar as like your OLS least square. Okay, so conditional least square of our ARMA model. Okay, similar to our like OLS or WLS. So WLS is the weighted least square, and the OLS is ordinary least square. Right, so the idea behind like this unconditional least square estimation of an ARMA model is very similar to the WLS or OLS of a simple regression model. Okay, so it's the idea is to find like the theta, phi and theta in order that can. The idea is basically to find phi and theta, so which is our coefficients in the ARMA model, so that can minimize the residual squares. So our model is like this: xt equal to alpha plus phi1 xt minus 1 plus phi2 xt minus 2 wt theta 1 wt minus 1. Okay, so that is our model. Okay. And let's assume this wt is a white noise. This ht some weight. So in the OLS, this weight is just equal to 1. Yeah, but in the weighted least square, you can just give some weights to this white noise. Okay. So based on this, we find okay, so all we need to do is to find phi and theta such that this criteria function, so this S phi theta, can be minimized. Okay, and this S phi theta is just the residual squares. Okay, so it's a residual squares. Okay. Yeah, so it's just very similar to the OLS, or I mean WLS in the regression. So the idea is just to minimize the residual squares. Okay, and to find this phi and theta, all we need to do is to take the first order conditions on this criteria function and set the first order condition equal to 0. And we can, I mean, in most cases, we can find a closed form solution of the phi and the theta. Okay. Yeah, so I think the idea is pretty simple, but to find theta and phi might be a little bit complicated by hand. But I mean, luckily, the computer software can help us to do all these things. Okay. Okay. Okay, so any questions about like the theories of the ARMA estimation? Okay. So now let me talk a little bit about like the properties of the estimator. So just like the estimator in the linear regression model, here we also want our estimator to be a good estimator. So we want to be unbiased, we want to be consistent, we want to be asymptotic normal. Okay, so or maybe a more ambitious goal is that we want our model to be efficient. Okay, so let me talk a little bit about like the properties of the estimators we have here. Okay, so let's start with the AR1 model. Okay. Okay, so the coefficient phi1 we get from our AR1 model converges like asymptotically to a normal distribution, where this normal distribution has mean phi1, so which is the true phi1. Okay, and here's the variance. The variance is 1/n times 1 minus phi1 squared. Okay, so from here we can see that this is pretty good. So we know that this is an unbiased estimator. The estimator is also consistent, and it also converges to a symptotic normal distribution. Okay, so this is very good. So unbiased consistent and asymptotically normal. Very good. Okay, and from here you can construct the 95% confidence interval for this phi1. So you can construct 95% confidence interval. Okay, so which is phi1 plus minus z alpha over 2. So this is like the standard normal distribution. Square over n. Okay, so that's the confidence interval. And for the AR2, people also shown that the estimator of this AR2 model is also very good. It's also unbiased, consistent, and asymptotically normal.
Did you mean phi1 in that first one?
I'm sorry.
Did you mean phi1 in that first one?
No, it's phi2. It's not a typo. It's just phi2. Yeah, so you don't need to memorize this. The ultimate goal is to say that the estimator is very good, a very good estimator. So very good estimator. Okay. Yeah, but the point here is that let's suppose that the model is actually AR1, but we fit it as a AR2. So what happens? Okay. So if the true model is AR1, we fit AR2. Yeah, we definitely know this is not correct, right? Yeah, if we know like the true model is AR1, but unfortunately we fit it as AR2, we know it's definitely not correct. But this is sometimes unavoidable in real applications, right? Because in real applications, suppose you know the model, there's like no means that you want to do the estimation, right? Because we do not know the model in real applications, in real data, then we want to estimate these models. Okay. Yeah, so this is like a typical thing that's in real applications. So suppose like the true model is AR1, but unfortunately we fit it as a AR2. So what happens? Okay, so two things. So first, so the phi2 hat should be 0. Okay, this is very easy to see because like the true model is AR1, that means the xt minus 2 does not affect xt. Okay, so if we fit an AR2 model, then the coefficient of the AR2 should be equal to 0. Okay, so when you like run this unconditional least square, you will find that this phi2 hat, or the estimator of this phi2, is equal to 0. Okay. The main part is that what happens to phi1, okay, or to be more precise, so what is the variance of the phi1? Because like the estimator of the phi1 should be a consistent estimator, but what happens to the variance of it? Yeah, that comes to your point. Okay, so the variance of the phi1 is, so this is phi2. Yeah, so this is phi2, not phi1. Okay, so the variance of phi1 becomes 1 over n times 1 minus phi2 squared, right? Just by using this formula. right? But we know that this phi2 is equal to 0. So this is just equal to 1 over n. Okay, so here is because phi2 is equal to 0, or phi2 hat is equal to 0. Okay. In contrast, if we just fitted this data by using an AR1 model, if we just use AR1, then the variance of phi1 is equal to what? Is equal to 1 over n 1 minus phi1 squared. Okay, so which is this very first formula. Okay. Okay. And since this phi1, we know it is less than 1 in absolute value. So that means this term is less than 1 over n. Okay. So the variance in the correct model is less than the variance of the incorrect model. Okay, so that's the key point. So the variance of phi1 in the wrong model is larger than the variance of phi1 in the true model or in the correct model. Yeah. So in other words, an AR2 to AR1, then the estimator of phi1 becomes less precise, right? Because the variance we got in this wrong model is larger than the variance of phi1 in the true model. Okay, so in says becomes less precise. Okay. Right. So that might give you a hint when you fit your model. I mean, yeah, when you fit your data to the model. So if you got a insignificant coefficient, then that might suggest your model might not be correct. You might overfit this model. Okay, so this is again basically the same idea of the linear regression, right? So in the linear regression, if you fit a regression and if you find the coefficient of a variable is insignificant, then what does that mean? That means that that coefficient or that random variable does not affect your y variable, and you should consider get rid of it. And here it's the same thing. So if you find a insignificant estimator, then you might think that estimator might not be very important, and I might get rid of it and refit the model and see what the new model does. Okay. Yeah. So I mean, this is like the theory behind it. So why you want to do this? So why you want to get rid of the insignificant variable? I mean, the intuition is that the insignificant random variable does not affect your y variable, does not affect your dependent variable. But I mean, the theory behind this is that I mean, in this case is this. Okay. the variance you got gonna become large if you wrongly fit the model. Okay, so any questions here? Okay, so just for the completeness purpose, I give you the asymptotic properties of the theta in the MA model. So again, you can see all these estimators are very good estimators. They are unbiased, they are consistent, they are asymptotically normal. Okay, and moreover, you can also use the same arguments in our AR, like the same argument in our AR model to see that if we fit like a MA2 to a MA1 model, the estimators of the theta 1 we got would become less precise. Okay. Yeah. And there are also theories of like the asymptotic normalities of the estimators of the ARP and the MAQ and also ARMAPQ. Yeah, but I won't cover those things here. This is just not that important for this class. Okay. Yeah, but I mean, the whole point here is that the estimator we got from this unconditional least square is very good. Okay, and most of are the same as the coefficients, the properties of the coefficients from like your cross-sectional linear regression model. Okay, so so now let me before moving to the forecasting, yeah, I think let me see, do I have I think I can finish everything. Let me talk a little bit about the forecasting first. And because I think like in your homework, you also have the forecasting problem. So let me do a little bit of forecasting and finish the forecasting next class. Okay, so. I will introduce the forecasting a little bit, and then we will switch to the R to see how we can estimate the model and how we can do the using R. So let's talk about like the forecasting. So the forecasting is very important, not only in time series, but also in like all econometrics. So we want to use like the our known data to predict some future values. Okay, so that is given x1 all the way to xn, what is xn minus 1, what is xn minus 2, and what is xn minus n. Okay, so that's our goal. So our goal is to use the observed data to make some predictions, or I mean here is to do some forecastings. Okay. Okay, so let's start with a AR1 model. AR1 model is this. And we have data x1 all the way to xn. We want to know what is xn minus 1. Okay, And I think the textbook used this notation. So it's x subscript is n minus 1 and the superscript is n. So that means xn minus 1 based on x1 all the way to xn. Okay, so then xn minus 1n, we know that it is equal to phi xn n, right? So so it's basically xn by using n observations plus wn minus 1n. Okay, so since xnn is observed, so we can just write it as xn. Okay. Unfortunately, the error part is not observed. So we do not observe the wn minus 1 given w1 to wn. So unfortunately, we do not observe this part. All right. So that says that to predict xn plus 1n is not feasible by just using x1 all the way to xn. The reason is that we do not observe the error term in period n plus 1. So that means we cannot do the correct prediction. So in practice, what people do is that we do this average level prediction or the expected level. So we take the expectation on both sides. This is not correct. This is gonna be the so we take the conditional expectation on both sides. Okay. So this is just phi times xn because xn is here. So we can pull the xn out of the expectation. Okay. So that's just the rule of the expectation. Okay. And the second part is just there because wn plus 1 given n, even though we do not know what is that, but we know it is a y noise. Okay, you can think it as this way. So that means the mean of wn plus 1 of n given x1 to xn is there. Okay, so that's just equal to phi xn. Okay, and in practice, we just call this the one step ahead forecast. And similarly, the two-step ahead forecast is xn minus 2 n. So now here's xn minus 1 n plus wn plus 2 n. So what I do here is that I plug in the formula of xn plus 1n, so which is the formula that I give in last slide, which is equal to phi xnn plus wn plus 1n. Okay, so I just plug in the formula of this, okay, and do this very simple algebra, and this is what I got. Okay, and we take conditional expectations on both sides, and we can get the two-step ahead forecast, which is xn minus 2n given x1 all the way to xn is equal to phi square xn. Yeah, very easy to understand. All the error terms are white noise, so their conditional expectation is equal to 0. And all we left here is xn, and the coefficient for that xn is phi square. Okay. And similarly, we can show the m step, right? The m step estimator is just phi to the power m xn. Forecast. Okay, so yeah, so that's the forecast of the AR1 model. And if it's an AR2 and AR3, or maybe a MA1 or AR-MAPQ model, so we can basically use the same idea to do the forecast. Yeah, but I mean, if your model becomes complicated, then the closed form solutions of your like M step ahead forecast is gonna be complicated as well. So I think we will, I mean, not what I think. So we will mostly like rely on the computers to solve this M step ahead forecast for us. Okay, so I think I will switch to the R and finish the R codes of the estimation and the forecast. Okay, so this example 3 is the estimation. Okay, so here the code that we use is called this S-ARIMA. So this would help us to do the unconditional least square estimation. Okay. And this is the data series, or the data we will have for this S-ARIMA model. So this is the diff of the log of the varf. So we take the we take the log on the varf, and we do this first difference. Okay, so this is, and the model that we have here is a MAQ model. Okay, so this is a MAQ, sorry, MA1 with without constant. So we assume that there's no constant here. Without constant, on this data series. So it's the first difference of the log varf. Okay, and if you run this, you can show that it has everything here. Okay, so the MA coefficient is this negative 0.77, so which is good. It's less than 1, so it's a causal model, and it's a valid ARMA model. And we can also find this is statistically significant. Okay, so let me write it here. Okay, so significant MA1 coefficient. Okay, valid. I mean, causal and invertible model. Okay, so this is what we can see here. It also reports you the AIC and the BIC, or also AICC, the corrected AIC. So you can record these numbers and maybe compare those numbers with your other models. Okay, and what's more important is that it gives you all this like residual plots just in this plot section. Okay, so this is the first is the standardized residuals. So you can see it's pretty good. Okay, so it's good residual plot. Okay. And you can check the ACF. So we see that the first leg of the ACF is a little bit like outside of this confidence interval, but the rest is pretty good. Most of them are within the confidence interval. Okay, so good ACF plot. Leg 1 not very good. Okay. And we can also say that this normal QQ plot. So the QQ plot, if you know that, let's just like describe whether your plot follows a normal distribution. Okay, so you can see this blue line. If you see this, there's a blue line here. There's a blue line just as what I mouse move. So there's a blue line. So this blue line is the normal distribution. And this dot are your data points. So if your data points are pretty much like overlap, and this blue line and your data points are pretty much like overlap with each other, then that means your residuals follow a normal distribution. And if it's like does not, like your raw residuals does not, match this blue line very well, then that means your residuals are not normally distributed. Okay, so we also have, so this plot is pretty good. So this is good normal residuals. Yeah. So remember that in our model, we want like our residuals to be a normal distribution, yeah, but not that important. I mean, you can like relax this assumption. Okay, residuals. Okay, and here the last is the LB statistic. We will postpone that. We will talk about that later. Okay, so overall, if you fit this diff log varf by using this MA1 model without constants, and you can say that pretty much everything is pretty good. So we got a significant MA1 coefficient. We found this is a causal invertible model, and all the residual plots are pretty much very good. Okay, so you can try those codes. There are some other models. You can try those models later. I will spend some time to discuss this model as well next class. But the idea is basically the same. You can like change the order of your model, and you can ask the computer to include the constants, and also definitely ask computer not to include the constants. Okay, so we will spend more time next class to talk about this. And the fourth example is the forecasting example. Okay, so this is again the S-ARIMA. So we use this recruitment data set. The order P is 2, D is 0, Q is 0. So this is a ARMA AR2 model. Okay, so we run this model. Okay, and it also gives you like all these things. Yeah, and you can see that couple of things are not that good. Okay, so first is that we check the AR1 and AR2, the coefficients are not very good. It's not a valid causal and invertible model. And you can also see that the ACF plot, we have some lags that are outside of this confidence interval. And more importantly, this like this QQ normal plot has not very good, and also your standardized residuals are also not very good. It has some like heteroscedasticity pattern here. Okay, but and also this LB statistic is not very good, but we will talk more about maybe next class. But here the key part is this forecasting. Okay, so here is that we use the model, and the code that we to do forecasting is S-ARIMA.4. So this is forecasting, and we do like 24 forecast. Okay, so let's see what we got. Okay, so the black dots are your raw data, and these red dots are your forecasting data. Okay, and these are the confidence intervals. Okay, so these shaded regions are your confidence intervals. Okay, so this is how you use the computer to do the forecasting. Okay. I'm sorry, so you understand what I mean here. So this is what we do the forecasting. So I will talk more about this plots next class, and also talk more about like this S-ARIMA model and this like residual plots check, and also the model selection next class. Okay, so but I think for now you can do the homework Okay, so if you have any questions, please let me know. So next class, we will talk more about this estimation and forecasting. Okay. Okay, so I think that's it for today's class. So thank you very much.
Thank you for meeting with us, Dr. Zhang.
Yeah, sure, yeah.
I basically just wanted to make sure that we found some data. I just want to make sure that I'm kind of not fundamentally misunderstanding what's going on.
Yeah, okay. Yeah, so just tell me.
Could you make me host so I could just share it with, just show it?
Yeah, sure. Okay, so.